Okay, so good evening. It's about 7:04 right now on a beautiful Thursday evening. It's a nice, cool 55 degrees. It's gonna get a little chilly tonight, but that's okay. It's springtime. Um, my name is Mark Burchfield. I'm a meteorologist here at the National Weather Service in Springfield. I've been here now about 5 years at the Weather Service office. Before that, I worked in emergency management with Greene County and then Webster County. Webster County is originally where I'm from and where I currently reside. So this area is home, and glad to call it my home and enjoy being here. So this what I want to talk to you all about is a presentation I didn't develop. It's kind of a combination of two classes. So we discuss severe thunderstorm structure, some of the basic characteristics of thunderstorm structures with different types of storms, and then also once we go through that, get into radar fundamentals. So you take the conceptual, what we really can see from a conceptual aspect, and then how can we apply it. Whereas, last night when we were looking at several different radar features, we'll try to go through and diagnose some of those. So let's first start off and talk a little bit about storm structure. So, and some of this, a lot of you, have already maybe seen some of this before. It's a good refresher. It's one of those things to where it's good to see every once in a while. And I'll talk about a few things that have come up over the last several years from the aspect of um, new research that's come out, new things that maybe we've always seen it this way conceptually, but we're now starting to see, well, maybe this aspect of the situation's a little bit different. So what we're looking at here is your typical thunderstorm, and we've kind of got three phases here. A lot of this typical thunderstorm you'll see, especially in the summertime, but we even had the beginnings of these yesterday. So as you can see on the left-hand side here, this is your cumulus. This is called the cumulus stage. So this is when you have a cloud that's got enough moisture in it and enough lift, enough to where they can get that cloud going to start rising. And if you've ever gone out and kind of watched these, sometimes it's really kind of interesting to do that. You'll see some of them really rise really fast, and some of them rise slow, and then they'll maybe stop rising or maybe start and stop. So it's really interesting to watch these develop. Once that cumulus cloud gets to a certain level, it rises about as much as it can. It will hit it'll hit a certain level where it begins to spread out or anvil out, sometimes, as they say. And then eventually at some point that air comes back down. So this is kind of that mature stage where you have a good solid updraft, some air going into the storm, and then at some point it drops back down, and this is your downdraft. You'll see kind of this neat feature here where it looks like it's kind of overshooting like a little top. It's called an overshooting top. Something that's really neat to think about and to realize with these is that whenever you can see this, maybe off into the distance, that's leaving the area or approaching, it's a really strong indication that it's probably a severe storm. And why is that? That's because it shows that there's such a strong updraft that it's trying to actually push even further. So it's trying to just continue going, even though it's reaching a spot where it typically can't go any further. So it's trying to overshoot. It's trying to continue growing. So if you ever see this where it's kind of overshooting, this overshooting top, you'll know that there's a strong updraft in that storm, and it's probably going to be a severe storm. But what comes up must come down. And so eventually the storm will just sort of, dissipate. Sometimes you hear it rain itself out. So this is that dissipating stage right now, where the updraft, I mean, there's so much, downdraft, there's so much rain cooled air that it's just cut itself off. It can't It can't get any more in there, and that's about all it can do. So let's talk a little bit about updraft characteristics. So we'll talk about a couple things here. You know, as we talked about before, there's two main parts to the thunderstorm. There's your updraft and your downdraft. So you've got your cumulus tower, that towering cumulus that rises up 40 to 50,000 feet. You have a rain-free base. So what is a rain-free base? It's an area generally right in the updraft region where there's no rain. It's typically dry under there. You can, you can probably see some sunshine. Usually, if you're looking off to the west, there's upward motion. It's an updraft in this area. On the right-hand side in this schematic shows where that air has come up. It will also descend. So that is your downdraft region. So if you were looking off to the west in this image right now, the sun in the background may be setting off to the northwest, you would see this downward motion, this downdraft coming down. So the downdraft characteristics, if you were in a downdraft region, if you were kind of stuck in here in that downdraft, it's going to be darker. You're going to be seeing a lot of rain, probably hail. It's really what you're seeing on radar, and I'll show you that here in just a minute. The rain and hail, everything that you're really seeing on radar with that particular storm, that's what is coming out of the downdraft region. And really, the downdraft region is where outside of tornado threat, that's your biggest threats are going to be in that downdraft region, because that's where your large hail is going to be. That's where those damaging winds are going to be. So let's take a look at that in respect to squall lines and supercells. So here's a case where we have a squall line running from western Missouri back into southeast Kansas. So you can pretty much see this as a linear. This is a line of storms that's moving in. Out ahead of it, however, you're seeing individual storms. They're just they're out there all by themselves, and they've got a different structure to them, and they just look a little different. These are supercells. These are the more intense thunderstorms. We did see maybe a few of these yesterday, not very many, but there was a couple of them out in Howell and Oregon counties, and then much more of them further to the east. You do have situations where you've got, I call them a hybrid situation, where you've got sometimes supercells that are merging into a line, or supercells embedded in a line, or it could get kind of messy. And it seems like we get a lot of those messy situations here in our area, where nothing's really ever clear cut. Very rarely do you have events where it's all supercell or all line. Sometimes you get a little bit of both mixture in there. So that squall line, just to kind of look at a schematic here, a couple different ways. You've got, let's say, this squall line's coming in. You've got your updraft coming into the storm. However, your downdraft is really strong. You're going to have a solid line of rain and wind as this downdraft just rushes out. So it hits the ground and just rushes and keeps going. Whereas, your supercell, this again is kind of reviewing that supercell case, where let's say you're looking off to the northwest. You've got your updraft here. Here's your kind of your rain-free base. You're not going to have any rain down here, but this is the region where you're going to have to watch out for a mesocyclone. So what is a mesocyclone? Essentially what that is an area of rotation above the ground. So the mesocyclone is not the actual tornado. Sometimes that can get confusing, where people may hear the word mesocyclone and mean that it's automatically a tornado. So hold on just a second here while it's saying I'm getting a connection issue. Just one moment. All right, sorry about that. Can everybody hear me now and see me now? Had kind of a little blip there. Thank you, Teresa. Saw your note there. Can you hear me and see me now, Teresa?
Yep. Yeah, I can hear you now.
Okay, great. What was the last slide where it died? Was it around in here?
Right there.
Okay. All right. Very good. Thank you. You know, it wouldn't be a day without some internet issues here at the Weather Service, but that's another topic for another day. So we'll keep going here. Get to the fun stuff here in a second. Just wanted to recap with our classic supercell. We were really talking about that mesocyclone, where the mesocyclone is not the tornado itself. So a mesocyclone is an area of rotation above the surface, well above the surface. We look at maybe sometimes between 5,000 feet and maybe 10 or 11,000 feet. That's where that mesocyclone is going to reside. So as you can kind of continue upward, your updraft, here's your overshooting top we talked about, nice cirrus plume here, and then your downdraft. So think about it from like a hail aspect, where you have water droplets up here that are below freezing, and the longer that hail can stay up in the storm before falling, the bigger it's going to get. So there's some things we look at there from a hail perspective of where's the freezing level. And if like right now, it's still early in the spring, so the freezing level is not as high as it would be in the summer. So right now, the freezing level in an afternoon is about 10,000 feet, whereas the summertime it's more 15 to maybe 18,000 feet. So the lower that freezing level, the easier it is for that hail to sit up there and grow and get bigger because it's below freezing longer. And the higher it gets, the more it has, the more potential it has to get bigger hail before it gets too big to where it just can't stay up there and falls back down. Here's a neat schematic on Tornadogenesis. So we've got a supercell storm. We've got a updraft, we've got a downdraft, but what actually comes together to actually make a tornado? What is that kind of that missing, that last piece of the puzzle? So for a long time, a lot of research has been out there about, you've seen maybe this hook echo or this area, this second downdraft. Essentially, it's a second downdraft that is behind the storm, and it's called a rear flank downdraft, or RFD for short. It's essentially where you have air that's able to not just go outward and then down, but it's able to actually wrap back around. So you have enough turning of the winds to where you can get that rear flank downdraft to come back in. And whenever you can get that to happen, you can get enough spin to create a tornado. This is whenever you have a rear flank downdraft, it just adds to that confidence that a tornado is occurring or it's likely to occur. Some people, chasers and those that are out there during and during the storm, watching the storm, if they're out in that rear flank downdraft region, sometimes they'll note that, we just felt a okay, and we're back. It's showing me now each and every time that it seems to be having that little blip. But we're back. And so we were on the Tornadogenesis image. The Tornadogenesis is really that kind of what I said, that last piece. What makes that tornado form? So if people and chasers that are out there, and they're very close to where a tornado is going to form, they've made note that this rear flank downdraft region, they'll feel this burst of air. Not really cold per se, as cold as it would be in the downdraft, but almost, kind of lukewarm, just sort of not super cold, but and very windy. And so when they're in that region, it's near the tip, near that hook, that's a good indication that they're in that rear flank downdraft region. You'll also note up here in this downdraft region that it's everything's spreading outward. So if you're in that region, you're going to likely be experiencing a lot of hail. That's your hail core. Chasers call that, hail, core punching. If you were to drive through that, you would never want to go through in that situation. But what makes that tornado is when you are able to get that updraft and that secondary rear flank downdraft to come together in the right spot here. Typically, if you do have a hook like this, it's going to be right here at the tip. That's your best spot for a tornado. So here is your Joplin supercell. So what we kind of talked about a little bit was, you could see here's your supercell, your downdraft region where a lot of your hail and stuff's going to be here. But you can also see where it comes back down and hooks in. This Joplin case was very messy because you had another cell that was coming in from the southwest that was merging into it. Been a lot of research and studies still ongoing, and a lot of people still wonder the interaction. Sometimes you have storms when they do bump into one another's or merge into, it can be destructive to where it kills the storm essentially. Then you have some where it's constructive, and it can really make the storm be even stronger. So I'm not sure if that was the case here. It could have been, but the thing you will see as we look at this, here's from a velocity standpoint, or a reflectivity standpoint. Look at the debris ball here, and we'll talk about that a little bit more. So what your radar is hitting here is a ball of debris. It's hitting large objects. If you were to look at this from a velocity standpoint, so we look at velocity. Velocity is really important. It's other than reflectivity, velocity is probably your second product or tool you want to look at. So in this case, obviously the Springfield radar is off to the east, northeast. So there's different color scales out there that some use. We've kind of got a standard one here, where these red colors, those are your outbounds. So your red colors is air, velocity. It's movement of air that's going away from the radar. Green is your incoming. It's coming towards. So you'll see right in the middle here where you've got incoming and outgoing, you've got a strong area of velocity, what they call a velocity couplet, or they're coupled together. Very strong in this area, and this is where your tornado is going to be. The other thing to note while I have it on this, you see this purple line in here, otherwise sometimes called purple haze. It was off to the west out here in Cherokee County, Kansas. You'll see this a lot of times. This is when, so the radar gets to a point where it hits certain areas and it can't quite figure out what is there. It can't quite figure out what speeds things are. It's pulse. It's the way the pulse of the radar is when it hits that certain spot. You'll see it's kind of a ring. So if you ever see this, that's sometimes also called range folding. So I'm not going to go into it in too detail, but it's definitely an area where you just can't really trust what you're seeing in here. It's kind of messy. And sometimes what will happen is it will have a storm that's developing or moving into this area, and that makes it very difficult to diagnose what's going on. So we can try to tweak some things with the radar settings here to adjust that, to maybe just adjust that purple ring outward or inward. But if you ever see that, kind of wonder, well, why is that purple ring in there? And it's only going to show up on the velocity. That's why. It's hitting a certain area it just can't quite diagnose. Once again, your schematic, just to reiterate, to beat a dead horse here, this is your schematic of a classic supercell. And to get a classic supercell, you've got to have, a lot of things come together. To get supercells in general, you've got to have a lot of good wind shear so that you can even get these updrafts and those cyclones to form. You've got to have a good environment. You've got to have enough moisture in place, even just to get clouds. So a lot of things have to come together. But if you are looking at a supercell, if you're looking off to the northwest here, you're always going to have your updraft region generally clear, not much going on, but this is before tornado develops, and then your downdraft region where you're going to have a lot of your preset. So let's take a look. Here's a good supercell example, a little video here of a supercell storm. This is an individual that's driving off to the it was driving off to the left or to the west there. Here's another one. I'll pause the first one here. So you'll notice a couple things. One of them, you've got a distinct feature here, likely a wall cloud. You've got an area of dark, likely rainfall and downdraft region here. So you can see clearing off to the west here. So you've likely got your updraft and then your downdraft. Let's take a look at the next one. Kind of the same thing. You've got that updraft off to the left here. It's going into the storm, and then your downdraft on the right. And so if you know that that downdraft is off to the right, then you'll always want to know if you're out there driving or spotting in it, you're not going to want to generally go towards that region. You're always going to want to stay to where that downdraft is kind of on your right, because that means the storm is going, it's going off to the right. It's not necessarily coming towards you. We kind of just did briefly talk about wall clouds. Those are not always rotating. So you can have a wall cloud that's there. This is at the base of the updraft region. You'll see, very distinct. If you're ever been really close to one, you're really gonna know that it's there. A lot of times, I think I do have an example here in a minute of what they call a scud cloud, or an SLC, a scary looking cloud. It's kind of ragged and it's just maybe low hanging. It's kind of ominous looking, but it's not as distinct as these. These are very distinct wall clouds. You just can't really call them anything else, because they're very clear cut, especially if you get close to them. And it's important for us to know that those are there, because we know that we've got a strong supercell storm that may produce a tornado, and it may not. Just because you have a wall cloud doesn't mean there's going to be enough rotation to get a tornado. But these are kind of what they would look like if you were to look at them up close. And what you're seeing above that is your mesocyclone. It's your rotation that's aloft in that 5,000 sometimes 10,000 foot range. That's where your rotation is. It's the big question is, can you get the rotation down at the surface for a tornado? Here's a really nice video of a wall cloud here. I'll go through this a couple times because it's really interesting to look at from this angle. A couple things to point out. You can see the rotation. You can see how these clouds are definitely rotating around like this. And then if you're from the back, if you're on the other side, it would be kind of, turning like this. So you can see that, that inflow coming in and causing that, getting some good rotation here. What's interesting also about this, near the ground, you can actually see a little bit of maybe dust, dirt, something that's getting enough spin near the surface. So this could be a situation where you do have a tornado that's occurring, and you're just not seeing the connection between the two. The actual condensation funnel, you may have that going on, or you may just have enough wind at the surface. This may be just before a tornado forms. So this would be a case if you were reporting this, it would be reporting a rotating wall cloud. It's not quite clear if there is a tornado there, but you can see you're making out something near the surface. You can also see how the dark color is here on the right-hand side. You can definitely see where your downdraft is, and so that definitely lets you know that storm is moving to your right. So you wouldn't want to drive to the right. You kind of want to stay where you were, or maybe go a little bit in this image to the left there. Again, just to kind of reiterate, you've got a nice wall cloud here. Your storm's moving off to your right because you've got your downdraft on the right-hand side, a nice strong rain-free base here, nice updraft and downdraft region. Talk a little bit about funnel clouds and tornadoes. Kind of highlight two things in this image is really interesting. One of them being, obviously, you've got a tornado in this case because you've got debris. You can clearly see your tornado there. Sometimes you get these tails, they call tails or beaver tails, that they kind of slope up into the storm. It's another indication that you're getting a lot of inflow into the storm. But a funnel cloud, it's just simply a cloud that's extending out. It's rotating, funnel shaped. It's attached to something. I think that's one clear thing too to point out, that it is a cloud that is attached. If you see something that's not attached to something, then it's kind of makes you wonder what, maybe it's a different phenomenon. But a funnel cloud is one, it's not reaching the ground at this point. But it's definitely, it definitely means that you've got some rotation. You've got the ingredients just about all there. So you can see in this one, you've got very difficult to see what's below that white funnel. You've got a lot of rain. It looks like dark clouds and a lot of rain in there. Very hard to discern without, getting closer, etc., that you have a tornado. It's just difficult. You could definitely see on the left-hand side the clearing, the updraft region, and then you could definitely see where your downdraft region is. So you've got your funnel here, but it's the big question, and you can kind of hear them in the background. They're trying to discern, is it on the ground or not? It's difficult to say because you've got so much rain there. And then they're also keying in back here, off to the left. Is this a secondary area? It's just difficult at this stage to call it that. It's difficult. It's never easy. And you notice a lot of these videos and images that I've shown you too, you're in a lot of flat country. Not always the case. The further you get into the Ozarks out here, it's hills, it's trees, it's just the terrain is very difficult to spot out here. So your tornado is pretty clear cut. You've got a violent rotating column of air that's on the ground. That's the main feature, and that you're able to see that because of really the debris that it's picking up. Here's one. Is this wall cloud, funnel, or tornado? Let me give you all kind of a second to take a look at it and try to decipher what you think. This is just a still shot. Franklin, what do you think? What do you think this is here?
I think it definitely looks like a wall cloud. It looks like there may possibly be something underneath it, but I think I'm too far away to tell. So if I was reporting this, I think I would just say it's a wall cloud with possible rotation underneath it, but I can't confirm.
Yep, I would say you're on the money there. You could definitely see something darker under it. This could be dust. It's hard to tell exactly what it is. But you could definitely see you've got a wall cloud here. You could definitely tell just to the left you're in an updraft region, and then on your right hand side here where it's darker, you can definitely tell what your downdraft is. But yeah, there is something there. It could be a situation where you're starting to get some air right underneath the wall cloud that's starting to ascend upwards. And that has been another area of continued research is, does the tornado always form from the top down, or is there more of an influence from the bottom up? So that's something to kind of we're kind of still wrangling is, which one of the components is stronger. But yeah, that's right on the money. That's exactly what I would report to if I was out here watching this thing. In a still shot like this, it's hard to tell 100%, if it's rotating or not, but it's I imagine it is in this case. Okay, cool beans. All right. All right, let's look at this one and take a minute to take a look at this image and see what in the world is it. And I'll pick on somebody else new here in a second. All right, Heather, what would you call this thing? What in the world is this?
Looks to me like a possible funnel cloud.
Okay. Yep. kind of it could be. It's hard to say. You could definitely see kind of your wall cloud in here. I think we can establish that, and then it's difficult, but you've got to kind of really squint, but you can see a little bit of another
Like it could
lowering.
be something that might be wrapped in rain.
Yes, exactly. It's dark in here also, so you kind of it's just it could be it's something in there. It's rain wrapped. It's just uncertain in there, and you're just at a long enough distance away to where you just can't 100% say. All right, cool. Thank you. So let's kind of go back into squall line here. Let's take a look at this real quick. So we'll look at a squall line two ways. So if you're looking at it from the radar view, and then if you're looking at it from a side view, if you were on the ground looking at this and you were looking north, you could see a couple features I want to point out. You point out is this strong shelf cloud. We haven't talked much about the shelf cloud, but it's something we see. Honestly, we probably see more shelf clouds here in the Ozarks than we do wall clouds, just because we get a lot more lines of storms that are able to produce that downdraft and shelf cloud than we do supercells. So in this case, if you had a line of storms like that one I was showing you in the radar image moving off to the east, you would see that downdraft is just pushing out, and it just continues to push off to the east. But out ahead of it, you still got air that's trying to go above it. So that's why you've got this shelf cloud that's kind of forming a little bit of a slope. And you'll see some shelf clouds that are really impressive with the slope. I almost, sometimes it's almost easier to call it like a slope. It's almost like a slope cloud because it's just so more than a shelf. It's very, very sloped. And that's indicative that you've got an air that's trying to punch and trying to go over it while it pushes off. So your shelf cloud is the leading edge of the strongest winds. So if you see a shelf cloud coming like this, you're likely going to have not a lot of time before those winds get to you. And what's deceiving in a lot of these cases is that you get the shelf cloud and you look right under it and you just don't see any rain or anything. It's maybe getting ready to approach you, but it's not, you don't see rain under it, but there's still a lot of wind with it. The shelf cloud, usually the rain can be 10, maybe 20 miles behind the shelf cloud because the storm movement, it can be so fast that the rain's just lagging and staying behind. Here's kind of a neat video of that. Now in this case, let me go back here. In this case, they're close together, the shelf cloud and the rain, but you can just see how this really comes in and just comes through really fast. The other thing to point out here is if you look at kind of the top right, early on, you're seeing air that's clearly going up and over it. So this would show you that this thing is moving off to the right hand side pretty quickly. Let's talk a little bit about squall line tornado threat. Squall line tornadoes are difficult. They're real. They're essentially tornadoes that form in a squall line and not in a supercell mode. Typically, your squall lines, and if you're going to have a tornadoes in a squall line, they're going to be difficult to see, almost impossible to see, because the storm is it's so much rain in it, and they're going to be rain wrapped. So if you're to be able to see a tornado in a squall line is going to be really difficult. It can be done, but you're just too close and dangerous situation if you do see those. We'll talk a bit more about those in a second. And it also comes to positioning. Just kind of wanted to summarize in this image your updraft region and your downdraft region. So you might have heard of kind of that right-hand rule, to where you always want to keep that downdraft region on your right-hand side, because that kind of points to where the storm is going, so it won't be coming directly towards you. So that's why these individuals are staying right here, because they can watch the storm as it moves off out ahead of them to their right, and not necessarily coming right towards you. You can also see in this image a nice tail cloud coming into the storm, indicating a really strong updraft. The windshield test, that's kind of another thing too to kind of keep in mind of that right-hand rule, to where you wouldn't want to continue driving off to the right. You'd want to keep going maybe off to the left or behind a little bit. You can see a strong downdraft here. So what I talked about a little bit earlier, this low cloud that's kind of hanging here, it's not really connected to anything. It's not real distinct. It's just a scary looking cloud, or an SLC, sometimes what they're called. We see a lot of reports sometimes that come through that these are wall clouds, or these are or even cases where these are called tornadoes. And typically, a lot of the general public will get calls, because it may come over a city or something like that, and they'll just say, "Oh, we're seeing this cloud. It's tornadic." Not. So this is just a scary looking cloud. It's just a low cloud. There's enough moisture near the ground where they're getting some cloud cover. But if it's not rotating, if it's not attached to anything, it's just kind of there, and we just try to kind of ignore it. It's not really going to induce anything. So let's go to this image here. You've probably all seen this one before. This shows you your 1, 2, 3, 4. Whereas if you were to position, or if you were a home spotter, or you knew that you have spotters located in each of these 4 positions, what they would expect. So if your spotter is in number 1, that spotter needs to know that they're likely not going to be seeing anything, because it's going to be raining hard, and the way this thing is moving, if it's moving off to the east-northeast, in this case, they're going to be right in line to get the hail. So they would be able to report probably a lot of hail, probably some gusty winds too from the downdraft. If you were in number 2, if the spotter was here, they're probably getting a pretty good look at the storm. And this would really probably be one of the best spots to be if the spotter was in this case. They can get a direct line to the storm. It's moving away from them. They can see what's going on. Same with number 3. They can get a good look. Spotter number 3 would need to be really cautious in case the storm turned off to the right a little bit. Spotter number 4 needs to not be spotting. Spotter number 4 needs to be in a shelter at this point. They're just, the storm would be right on top of them, and it'd be pretty dangerous. So we talked about the right-hand rule. In your spotting, try to keep that shield off to your right and clearing to the left. Kind of gone over that. So at this point, before I get into the radar fundamentals, more of looking, we've talked about the conceptual stuff. Now, applying more of the radar fundamentals, I'm going to kind of open it up. I've been talking for about 45 minutes or so. I'll open it up to any questions about anything we've talked about, or if you've got anything that you want me to go back to. Let me just unmute everybody here real quick, and I'll let you ask any questions or anything like that. So, okay, does anybody got any questions for me, or anything want me to go back to, or any comments or anything?
I have one.
Yeah.
Back to the shelf cloud where the rain was catching up to the front of it. Would that indicate that it's cutting itself off with the cold air?
Would that be like this image here?
No, it's the other one where it was harder to discern the cloud from the rain. That one.
That one? Yeah. I think that is the case there. Because eventually it gets even harder to discern because it's, I mean, at this point, it's not even, it almost looks like it's going off just ahead. It's not coming really towards you, but yeah, you could see it likely is cutting off the inflow. Eventually with time, you're losing any of your inflow in here. It was much more prominent. And you can even see, I think, especially towards the end, there was a stronger push off to the right-hand side. So I think just with time, it just cut off its inflow and it was just racing too fast.
Thank you.
Yep. Any other questions or anything that stuck with you there before we go on?
When you're seeing the cloud formations, what does it look like on radar versus what you're seeing on the cloud formations?
Okay, for as like so like
that image?
Like this one here?
No, the one that I identified that had the question, that one. What would that look like on radar?
So what this would look like on radar, let me go. So what it may well look like, I mean, you may have a storm that looks almost identical to this, especially you're going to have, you've got a wall cloud and you've got a good inflow and downdraft region. So what you probably are not going to see is this hook where it's like all the way around, like where it's hooked all the way around. What you may have is just more of a little appendage that kind of drops straight down. The way it kind of wraps around all the way around, that indicates that you've already got the funnel or tornado going. What you've got in that one image is you've got a wall cloud, but you've not had anything to punch it all the way through and get a tornado formed. So you could still have something like this. It's just probably not wrapped all the way around yet, quite like this image.
Okay.
I don't know if I could find another one. Go back here. Definitely not that. Yeah, a lot of these produced. So it would, I mean, you would probably have just a, you would really be most prominent right in the appendage or right near the hook. How far it's wrapped around and not would be. Another good thing on radar would be in the velocity. So what you would be seeing in a velocity image, if you were to look at the velocity, you wouldn't be seeing a couplet like this at all. So you would just be seeing, probably just a general, maybe some broad rotation, nothing quite distinct like this. I think the velocity product might actually be the best one to look at to really see, is there anything rotating or not?
Okay, and that kind of answers my next question with the squall line tornadoes. When you're looking at that squall line on radar, would it show on radar that there is a tornado embedded within there?
Yes, and so that'll be the next section I get into. We're going to show several examples of, situations within the line. Where exactly in the line is the spot for the tornado and why, and it will show you kind of where. So because there are spots in the line that are going to be more favorable for tornadoes than others. And so that's been a huge amount of research that's gone on over the last 10 years where we've, had, and a lot of it's because we've had a lot of these lines come through and have had a lot of events where we've had these tornadoes in these lines. So we've been able to diagnose them, and I'll show you here in just a few minutes where those are at. Any other questions before I keep rolling? Okay. I'm going to mute here, and we are going to kind of roll into some radar stuff. All right, here we go. So kind of talking a little bit about radar. Here's kind of an image showing where all the Doppler radars are in the United States. There's 100 and CONUS, even Hawaii, Guam, Cuba's got one, Puerto Rico, and several up in Alaska. So 156 of them scattered across the United States. It's really easy to see where you've got very good what they call radar coverage. And there's very easy to see where there's not much radar coverage. You get out here in the mountains, and it's hard to see a lot of these locations because there's just not very many radars out there. Then even in Missouri, I'll show you here in a minute, just a lot of areas where it's difficult to see what's going on near the ground, even though you've got some radars there. But it's just kind of interesting to see where they're all at. And you could definitely see where there's more of them. A lot of them in the central U.S., in the Tornado Alley regions, and then several out there on the coasts. Here's ours, image of ours here in Springfield. You've probably seen it over times. We've had these, upgrades. The radars, the whole system, United States system is going through a big upgrade. You think of the 88D, WSR 88D. Well, 1988, that's when these were really rolling out and going. Well, over the years, we've had to just imagine all the machinery and gears, pedestals, all the equipment that goes in here. And just remember that radar is always turning 24 hours a day, 365. You think about that many parts turning, we can make it go different speeds to keep all this stuff running. And that's just the hardware part of it. You think of then the software and all this stuff. It takes a lot of power, a lot of power to keep it going, a lot of upkeep. And so I think as far as the one here at Springfield, our next big upgrade is going to be on some of the gears inside. I think it's going to be next year, and that will be where they actually take the dome off. So they have to take the white ball off and with a crane move it to the ground, and then there's a pedestal inside that makes everything turn. And the pedestal is the part that has to be replaced. So that's going to be coming next year. I think it's like a week or 2 week long where it'll be out. But that's just something to look forward to next year. And with them replacing that, keeps that thing running better for the next, hopefully 20 to 30 plus years. So how does this thing work? So the radar sends out a pulse. It sends out a pulse that it's not just looking in the horizontal, it's looking in the vertical. It's an outbound pulse of energy, energy where when it comes out, it's a high amount of energy, but once it hits, the longer distance away, it loses some of that energy. So it's really going until it hits something. So if it's hitting rain, it's hitting hail, it's hitting debris, what it will do is send that image back. So it reflects back to the radar. And then we can actually see, this is the end result. This is just an image here from southwest Oklahoma in the northern parts of Texas, where you can actually, you can see what you see on radar is what in a scale, a dBz scale, what intensity, what you're exactly seeing. Your reds, pinks, it's likely going to be either very heavy rain or hail. Then your lighter colors, and some of this is likely ground clutter, which we'll talk about. So we're talking about interrogating radar, getting down in there and taking a look at all the features. These are the two products that people are most familiar with: reflectivity, what is being reflected back. This is a Supercell case, clear Supercell case here with a hook. Reflectivity is always measured in dBz, and you'll notice too, sometimes there are different scales. So you'll maybe see on TV the reds are in the 50 to 60, sometimes the reds are in the 60, on. So this scale can be adjusted. So just kind of be aware of that. Sometimes you may see, well, why is it, white and pink here, and what I'm seeing on my app might be different. So that's something to keep in mind. Also, the storm relative velocity. So this is the velocity image, what the wind is going towards and away from the radar. That is one of the most, other important tools to look at. And it's always measured in knots, not miles per hour. It's always measured in knots. And you can see which would the inbounds, kind of the greens and the blues, and your outbounds are typically going to be in a red to yellow color, depending on the exact scale. Here's a neat image here too when we're talking about looking at radar imagery. So take, for an example, your pulse, your radar, when it's going out at a certain angle. The lowest angle that it can go out is a 0.5 degrees. However, the radar, once it completes that scan, then it goes out at 1.5 degrees, it comes back. Then 2.4, it comes back, and then 3.4. So you can see all these different elevation angles all the way up to 19.5, which is the very last elevation angle. So we can get a good look at the height of the storm from the surface up to about 70,000 feet. But what's difficult is when you get further out in distance from the radar. So let's say you get out, 60 miles east of Springfield, 80 miles east of Springfield. You're not going to be seeing what's going on at the surface. You're going to be seeing what's going on about 8 to 10,000 feet. So especially it gets really difficult when you get out east of Douglas County. You got into, especially when you get out into Howell and Oregon, Shannon counties. We're looking out in this range where we're seeing things between 8 and 10,000 feet. So it's really difficult to know what's happening near the surface. Think about it from a thunderstorm perspective here. That's out in that range. It's further away from the radar. The radar will be scanning the storm and taking a look and diagnosing at all these different levels. So don't always get stuck and always think of looking at the lowest, very lowest scan, because you're likely missing some key things that are going on above. Hail core in this example. What we'll be looking at in supercells, environment kind of like yesterday, where we weren't really looking at a huge tornado threat, but we were really concerned about the hail threat. We would constantly be looking at these, in this case, these 2.4, 3.4, 4.3 scans to see, what kind of reflectivities do we have in this region, because that's where your hail is going to be if it's strong before it comes down. So the further away you get from the radar, it's difficult to know what's going on near the ground, but you can really get a good idea of tilting through these different elevation angles. You could do this if you've got, on GR, it'll let you, if you've got GR program, it'll let you go up. You can go up in the different, either by using your key, up key, or just selecting which elevation angle to look at is really important. The other thing we can do on our end, let's say that we're really concerned of a tornado and we want to just, instead of scanning way up here, that's time wasted where we really need to be scanning here. So what we can do is tell the radar, hey, just keep scanning this area. Just keep scanning it. Don't scan any of this, just keep scanning this. And so that's why sometimes you'll see the data's maybe coming in a little bit quicker sometimes than others. If you have GR in the bottom right-hand corner, it'll say like sales 1, 2, or 3. And so the higher number we increase that, the quicker that thing's scanning this lowest area. Sometimes we want to know more what's going on up in the hail core, so we'll tell it to scan faster there. So let's take a look at one here. So this is from May 22nd of last year. This is a classic supercell. We're looking at Dade County here. We're looking at Golden City, Lockwood. The radar at Springfield would be back off to the southeast here. So if you're looking at GR, radar, or your, whatever radar app you wanted to use, and you let's say you had the 0.5 degree slice angle pulled up here. And so at this spot, in southeast Barton County and Dade County, we're looking at about 2,900 feet. So we're never really truly going to be looking directly at the ground. I mean, you have to be really close to the radar to see that. For most of the area, you're going to be looking at the lowest scan a couple thousand feet. So you can see a clearly defined hook echo here. That's with likely tornado. We'll look at here in a minute. But you can also see this this pretty good hail core over here by Golden City. This is on the lowest scan. Let's go up. So let's go up into the storm. So we're looking at the 3.2 slice now, which is at 13,000 feet. So between 5 and 10,000, give or take, is kind of the area of that mesocyclone where you've got a lot of rotation aloft. And this would kind of be getting to the higher end of that spectrum, but still close to there. You could see where that strong hail core is at that level, right around Golden City area just to the north. I'll bring this up again here in a minute. You'll also see an area where there's nothing here. It's just a region of nothing. So that's important to look at. We'll look at that here in just a minute too. Let's go up to almost 30,000 feet. We're at 29,800 feet. This is the 8 degree slice. That it shows you right where the hail core is, right over Golden City. So it's a little bit further east in the higher scans. And there's a reason for that. We'll look at that here in a second. But this is what it would look like at that level. Go up even higher. We're almost up to 38,000 feet. It shows you where that hail core is still strong, right east, just northeast of Golden City. So if we were to do a cross section, and these are really important to look at. So if we're looking at this storm, we're looking at it kind of in a three-dimensional view up into the storm. So we're looking, up. Here's 10,000 feet, 20, 30, 40, 50,000 feet. And then we're looking at what the reflectivity is at that level. So you could see here, it fits conceptually the classic model. You've got your updraft region and then your downdraft, strong downdraft here. And then this area in between where there's really nothing there. So you could see that you have 60 to 65 dBz values, strong, really high values that are up pretty high. This is up at 30,000 feet and you have this strong of a signal. That means there's some really strong hail in there. So this is sort of something that's to kind of think about too. Warning tip. So hail that is equal to or greater than an inch. So a quarter, hail to the size of quarters, kind of that threshold we use for severe storms. It's usually going to occur when you have 55 dBz or higher that exceeds the minus 20 Celsius level. Well, you say, how would you ever figure that minus 20 Celsius? How do we figure that out? So let me go back to that. To figure out where the minus 20 Celsius level is, you really can't necessarily do that straight from the radar. What you would need, that's one of the reasons why the balloon data is so important. So if you pulled up our weather balloon data and all the temperature data all throughout the atmosphere is on there. So typically at minus 20 Celsius is around between 20 and 30,000 feet on average. Yesterday, the minus 20, where it was minus 20 Celsius, was about, I think, 22,000 feet. So in this case, let's say the minus 20 level was about 22,000 feet. We've definitely met our 1 inch, criteria, because 55 dBz or higher is exceeding the minus 20. We've actually got much higher levels there. So this is telling us that you have really big hail that's up in this storm that's just sitting up here waiting to come down. So this would tell us that we've got some big hail in there. So that's just something to think about, a good kind of thing to maybe take away when we're talking about hail. And what I would say to this too, the higher number you get, if you've got like 60 to 65 dBz that exceeds the minus 20 Celsius level, then your hail is likely going to be closer to golf balls, if not higher. So let's look at some reflectivity and velocity signatures. Here's that Supercell signature hook echo. First thing that stands out, hail and heavy precip there. Zoom in on it. You could definitely see the rotation here. I mean, this is a very, very strong couplet where you have winds that are just racing towards you and away from you. So this is a strong rotation here southwest of Golden City. This would be called a tornado vortex signature. That's essentially a signature where you have enough speeds going in opposite directions to get that rotation. If you have like GR, some of the icons on there, you may see a little triangle, upside down, tornado triangle there. Here's another classic example. This is of March 3rd of 2019, and we're looking at Lee County, Alabama. Sometimes it'll show a debris ball. I know Joplin showed the debris ball. So what this is where the radar is sampling very high values of debris. It's not going to be hail. So this would be a region where you're not going to get hail in this region. So it's obviously something else much larger. So this is telling us that this is definitely big objects like boards or debris, cars, whatever. This is really strong debris. This is easier to see when it's going over more urban areas. When it's out rural, it's much more difficult because it's not as likely to hit bigger objects. That is your debris ball. So let's take a look at this. Let's go back to our storm because I wanted to talk to you about something called a weak echo region, and I kind of highlighted it a couple times when we went through this. A weak echo region is sort of just kind of what it indicates. It's an area where you just don't have hardly any reflectivity, where it's kind of a void. If you were to go up, so we went up to 13,000 feet, we could still see that void there. It's still there. There's just nothing there. Kind of a hole. Sometimes you'll hear it referred to as a donut hole. If you may see that verbiage come across. But then at that point, it's called a beware, a bounded weak echo region, because it's bounded up higher aloft. In our 8.0 slice here up to 30,000 feet, there's your hail core right over Golden City. And then you go up to about 38,000 feet, your hail core is a little bit further to the northeast. Well, why is that? That is because your hail core is up here because you've got really strong wind shear. And so you have a good strong tilt. You need the storm to be tilted. That's because the wind is much stronger the higher you go up. So it's causing the storm to tilt like this. And you can see this weak echo region. This is a region where there's no precip. What these indicate, if you see these, it's a good indicator where you have definitely a severe storm and definitely a storm with a really strong updraft and one that really needs to be watched closely for tornadoes. Let's talk a minute about a three-body scatter spike, TBSS. So what you'll get sometimes is when the radar sends that energy out and it hits hail, what it will do in some cases, that energy, instead of coming directly back, the energy will go straight down. It'll be deflected right to the ground. Then that energy comes back up to the storm and then back to the radar. Kind of makes a loop down and back. So what would this look like if you're looking at it on radar? And I know probably many have seen this before and wondered, what is that? So you could see in this case on the left-hand side, here is your radar, the red circle. And you think about it, your energy the energy of the radar, the pulse, it's hitting all this hail. It's being deflected back. It's being deflected to the ground, then back to the storm and back. But what it leaves is this return that extends further out. And when you see this, you think it's just, this, it doesn't make any meteorological sense why this would be there. And that is an artifact of that it is hitting. You definitely know that it's hitting hail. You don't always know, just because you have a spike like this doesn't always indicate how big the hail is. But if you are getting a spike like this, as you can see on the one on the right-hand side, to where it hits that hail core, and you can see how it extends out off back here. It definitely tells you that you've got, you probably do have some large hail in that storm. But that's what that is, a 3-body scatter spike. We'll talk a little bit about rotation. We measure velocity to detect circulations and different features. Here's kind of an example showing, from the radar, showing that rotation. Sometimes you have rotation that's clockwise. Sometimes you have rotation that's that's not clockwise. Sometimes you have divergence. So here's a case where you're looking and you're seeing all these velocities going away, and a lot of them coming towards you, but not necessarily convergent. So this would be a case where you're getting a lot of divergence, and that's not really conducive to tornadoes. Whereas in this case, where you have convergence, where they're converged together, the more convergent you have with rotation, the higher chances you have for a tornado versus divergent rotation. So here's something to kind of look at, if you're seeing, and I'll walk through an example here in a minute, the chances of tornadic development increases in a storm, if it develops rotation that, has convergent rotation. So going back to that, there's a divergent rotation where here's your radar, and you've got more of your couplets going away versus toward, or coming toward versus away. That's more divergent. Here's convergent when they're much closer together and they're coming right at each other. They're converging. Take a look at that here. Give an example of the Golden City storm. This is at 3,000 feet. You can see this convergent rotation signature here. That's just just west of the radar. Let's go up to about 11,000 feet. You could still see this rotation, strong rotation. So here would be an example of divergence. Your reds, remember, are your outbounds going away. Your greens and blues are your inbounds going towards. So you'll notice that you don't have any convergence here. Everything's going away from each other. So that would be divergence, where here they're going more towards each other and they're very close, whereas here it's more divergent. Everything's going away from each other. It's very important to look at this divergence because this can give us an indication on how strong the storm is aloft. So here's kind of another big takeaway that we look and things that we look at. So the stronger storm top. So storm top divergence. How would you even find that? You generally would want to look at in the bottom right hand corner. Go to the very top scan of the storm. Go to the velocity on it. In this case, it's about 50,000 feet, probably 8 to 10 degree slice. And what you would want to do is calculate, what values is the red, what's the highest value of the red and highest value on this side, and divide them. And that would give you the storm top divergence. Or if you have around 75 knots or more, then the potential for your hail goes up. Let's talk a little bit about pulse thunderstorms. Pulse thunderstorms are ones that very typically slow moving. Generally, very small cells that form in the heating of the day, typically in, typically summertime, but you can get them late spring and early fall, where storms bubble up in the mid to late morning, afternoon, rise up. They typically have a strong updraft at the beginning, but then they rain themselves out, where you get a downdraft that basically cuts it all off. Pulse thunderstorms are notorious for producing small areas of damaging winds. You can get some hail out of these pulse thunderstorms, but typically in the summertime, the freezing level is so high that it's very difficult to get hail at that time. Typically, you're getting just a downburst, a quick downburst of winds in these pulse thunderstorms. And you typically never, it's very difficult to get tornadoes in the pulse thunderstorm environment. Bow echoes and squall lines. We'll get into kind of some squall line tornado topics here. So here's an example of a storm, just a single cell. It's just an echo, a storm that developed. With time, it begins to bow out. You can see kind of why here. These your winds are curving it inwards, where you're getting a strong bow that eventually pushes through, and you can even get kind of what they call a comma head, where it rotates up here. Your strongest winds with these bows are going to be right at the apex, right here. In this region. That's where your most damaging winds are, because you've got enough winds coming in, from behind it and coming straight down to the surface. This is where your highest winds are going to be with these bows. So let's take a look at these. Here's an example of a squall line that is from about Stockton down to Arcola and extends down here, Jasper and Carytown. Couple things of note here. You can see out ahead of it, looks like you've got an outflow boundary already out ahead of this. So that tells me that this storm has already pushed out some really strong air that's already made it out ahead of the storm line. But here is your bow echo. You can see this V behind it, where you don't have very much. Whereas back here, you've got your yellows, and then you go to basically almost no reflectivity, and then you've got more reflectivity here. So back here, that's a signal that the air has come back in so fast behind the storm, it's punching through and it's bowing out. This is where your most damaging winds are going to be. These are kind of the features we just kind of talked about there. Now, and so if I was on, if I was in this particular case, if I was concerned about severe weather, damaging winds, I would be most concerned here in northern Dade and southern Cedar counties. Would not be as much concerned down here because you don't have much of a bow. I would be most concerned in the southern Cedar and northern Dade counties. Not necessarily for tornadoes at this point. And we'll get into that here in a second, mainly because your outflow boundaries got pushed so far out ahead. That really hurts things for tornado development when this gets further out ahead. We'll talk about that again in just a second. Here's another example. Here's a strong squall line from Greenfield down to Miller, Mount Vernon, Freystadt. This is from August 19th of 2018. The radar is off at Springfield, off to the east. You can see from two views. You can see this bowing out here, northeast of east of Mount Vernon. If you were to look at it from a velocity perspective, you'll see how your values go from just these light greens to these blues. So here's where your strong winds are, and we're pretty close to the ground here in northern Lawrence. We're probably 1,000 feet or so off the ground. So this area, northern Lawrence County, in the bow, whereas where I would be most concerned about damaging winds. Right in here. So kind of another slide to bring up, warning tip, the strongest winds associated with the bow are going to be near the apex. Going to be right near where it's bowing out the most. That's where the most concern is. So we're going to take a look at the May 21st, 2019 Mansfield to Hartville tornado. This was a tornado that developed along a line. So this is a QLCS, quasi-linear convective system. You'll hear that term QLCS mentioned quite a bit. That means it's generally a linear or quasi-linear convective system. And they may not always be very long. They may be short lines. They may be big, long lines that extend hundreds of miles. But they're more linear. They're not an actual supercell. So here was a case where you could kind of already see one thing that sticks out here just to the north of Mansfield is what we call a nub, a notch or a nub. You can just see where it just kind of sticks out there. This is an area where you've got inflow, you've got air that's coming into it, and you're going to get just enough spin for a tornado just north of Mansfield. Another feature, if you'll also notice just west here, you'll see where you also have another notch. That's another good key feature, that you have air that's come in from behind. So you've got an inflow, rear inflow notch and a front notch. So this area, if I was in this whole line, this is the area to watch out for a tornado at this point. Not necessarily the further north you go or south you go. Right now, this would be the spot to watch out for. If you were to look at it from a velocity perspective, here's what you're seeing. You're seeing that area north of Mansfield, where you've got your inbounds and outbounds. You've got a little couplet here. This is your problem zone, just north of Mansfield. And this is what they call that mesovortex. Mesovortex or mesovortices, they occur with squall lines. They produce tornadoes, it seems like virtually every year across the area. We get a lot of squall lines with these mesovorts that occur all the time. One thing I will note too with these mesovorts is that it's very difficult to see these the further away you get from the radar. So the further out you get out towards West Plains, Houston, Salem, and even west. You go out west towards Joplin and Neosho. It's difficult to see these because the process that develops these is really in a layer between 5,000 and 10,000 feet. And so, of course, the further you get away from the radar, you're not going to be able to see at that level sometimes. So it's much more difficult to see. So if you're within 40 to 50 miles of the radar, we can pick these up fairly well. But if you're further away than that, it's just really difficult. And that goes into the limitations of the radar. Ground clutter, radar coverage, topography, timing of the scans. So I talked a little bit about this earlier, and the radar's constantly scanning. It's always scanning. It's just typically scanning at a different level all the time. And then you have other features too, what's called side lobing, where the radar is sending a pulse, but it's only hitting the side of an object instead of the whole object. And so you're not really seeing the whole picture. These are a couple limitations. So let's look at a couple of dual pole radar signatures here. And what I mentioned previously with dual pole, you're not just seeing the horizontal, but you're seeing the vertical. So we're able to discern what the actual, a little bit more about what the shape is. Is it really hail, or is it more of just a big raindrop, or it'll even detect more of a snowflake. So let's go back to this here. Here's a product, your bottom right-hand side, that we want to always be familiar with and know a little bit of what it is. It is called a correlation coefficient, or CC. It is essentially a tool to discern what the size of the object is. And so I don't have the scale on here, but it goes in a scale from like 0 to 1, with the lower values in a blue to yellow color. The highest values, which are a 1, are these red colors. And so what you always want to know, if you see an area like this where you've got a really strong rotation couplet, and then look at that same spot, but on the correlation coefficient, you'll see it shows up at this blue-green spot. What that is depicting big objects. It's hitting some pretty big objects there, and that is likely, most likely debris. And so we can use this, what we call a tornado debris signature, or TDS. It can be used to basically let us know and confirm that, hey, we've got a tornado on the ground. It's currently on the ground right now, or it has been and did some damage. So this is a really powerful tool. You'll notice too that, look up here off to the northeast. Oh, well, we've got these low values here. Well, always do kind of a match. Well, there's no couplet there, so it's not hitting actual objects there. You always have to match it up to where the velocity is. So just to kind of reiterate there, another good tip, these TDSs can be used. So if you see us message radar confirmed tornado, radar confirmed tornado means that we're basically seeing that TDS, that the tornado has lofted something into the air. So let's look at August 19th, 2018. This was a really active event. You can see this line of storms goes from Vernon County all the way up, all the way down into Barton, Dade, Lawrence, McDonald, Newton. But you'll notice several areas where there may be bowed out a little bit more than others. So these are going to be some areas that we want to pay attention to a little bit more than the whole line. So if we just want to look at this whole line and find out some areas that we want to watch for damaging winds and tornadoes, it's going to be these areas close to these bows. One in particular, just to the north of this bow here, near on the Barton-Vernon County line, strong circulation developed north of Milford, and did produce a mesovortex. This was an area that did eventually produce a tornado. So right near these bows, or maybe just to the north, or either, those are the areas where you really want to key in on and watch for areas of rotation. Here's where it surged really closer to Springfield. And so you can see how on velocity and reflectivity, it almost matches up. The line here matches up perfectly. So we call this balanced. This means that this line of storms is balanced. It's the downburst, the downdraft is not going too fast and cutting off the inflow. It's moving at a steady state. And so these are dangerous because you have a higher chance of getting more of these little circulations near these bows when it's more steady state like this. Here, this was also a unique case, a hybrid case, because you had both events going on. You had a supercell storm that developed out ahead of the line. You can see down here this tight rotation. This storm actually started down here in Berry County and worked its way due north, while the whole line was moving east. The storm actually eventually got kind of sucked up into it here. I think near Billings. So let's look at this supercell out ahead of the squall line. You'll notice a good hook echo here. You'll also notice what is likely a debris ball. If we were to put on the velocity, really strong circulation just southeast of Aurora, matches right up with the debris ball. You're almost, dead confident that is a tornado ongoing right now. You've got convergent rotation and a tornado vortex signature here. To get that confirmation, maybe we've not had any reports yet, we can turn on the correlation coefficient, the CC, and look, you can see exactly the same region. You've got your very low values there, blue, green, tornado debris signature. Therefore, the tornado is on the ground there, and it is doing damage. This event, we had 8 tornadoes, multiple wind reports, and this was an EF1 tornado that went through Aurora. So let's, we're getting really close to the end here. I just wanted to wrap up with a few questions. I'm going to unmute the lines here as we kind of go through some of these, and let's take a look here. Unmute everybody. So the question asks, what do the two areas A and B represent on this image? And let me make sure I've got everybody unmuted that wants to be unmuted. Some might be self-muted. All right, everybody, so I've got you all unmuted here. What do you think A is?
Precipitation.
Yes, it is precipitation. What do you think B is?
Ground
Ground clutter.
Ground clutter. Yep,
Ground clutter.
you're right on the money. A is some sort of light preset, maybe some, some sprinkles or some light showers. B is definitely ground clutter. You will notice some nights where we have more ground clutter than others. A lot of that has to do with what we call an inversion, where the radar beam, it may hit some clutter near the ground and it may come right back down, and sometimes it may scatter out and you won't see the ground clutter. But nights where there is a really high amount of ground clutter, that's a good indication that you have a strong inversion, or also known as a cap, where the air is warming as it goes up. So that's kind of something too. If you start a morning out where you're seeing a lot of ground clutter, well, you've likely got a pretty strong inversion going on. But definitely just wanted to highlight the two differences there in that. So let's go on to question 2. What is the feature circled on each image?
That would be a TDS, wouldn't it?
Correct. Yes, Franklin. Yep, that would be a TDS. So what kind of gives that away here? You've got, we're looking at correlation coefficient, and we're also looking at that compared with, on the right-hand side, you've got velocity couplets there. So you've got a tornado debris signature. You've got debris that's being lofted up into the air. Something I'll bring up too, when we're looking at CC or correlation coefficient, sometimes, let's say in this one on the bottom right, eventually you'll still see the debris lofted, but the signal the velocity signal's gone. And what that means is that the tornado's done, but you're still seeing the debris that's still 15, 20,000 feet in the air. So this was actually the Jefferson City tornado. So you could see this storm was actually moving east-northeast. You could see the debris ball as it approached Jefferson City and then eventually went into Jefferson City. So and this was really one of the main reasons they were able to issue that tornado emergency with enough time, is because they were able to see this thing way back here and already get an idea that, hey, there is a tornado on the ground heading towards Jeff City. And there is also what they call a correlation between how high up you can see the TDS. So if you're ever looking at CC and you want to look up in the scans to like 0.9 or 1.3, you could see how high this TDS is. And so the higher this TDS is, the stronger the tornado is going to be, because it's lofting that debris even higher. And so in this case, the tornado was lofting debris up to like 20,000+ feet, and that's very high. And so they were able to get that tornado emergency out because they knew that the storm was producing a large tornado. So let's move on to question 3. We're looking at April 26th of 16. this was a strong bow echo that was moving into St. Louis. So the St. Louis radar is here in Weldon Spring. And the question asks, what does the dashed line kind of represent in the two radar images here? What is this kind of, what would this area be?
Be a bow echo, wouldn't it?
Yes. Yes. I don't know who answered that. I didn't catch the name, but
Jim.
Jim. Yeah, Jim Bauer. Yeah, Jim. That's your bow echo here. That's where so you've got a QLCS, quasi-linear convective system, but you've got a strong bow here, and you can also see back behind it where the velocity really cuts out. You can kind of see this V here. It's getting punched in. So this would be the region where I would be really concerned about the damaging winds and potential tornado even. As you can see, you kind of got a little nub here just southwest of Newmel that went off that direction. Let's look at this one. This one is May 28th of 2019, so in the evening near Lawrence, Kansas. This is looking at the half degree. The radar was off to the west, so it's cutting, it's looking at it this way. What type of rotation is seen in the circled area kind of on this? What type of rotation do you think is occurring? You think it's more convergent or divergent?
Convergent.
Yes, that's correct. More a convergent circulation. And yes, the other answer to the question is tornado on the ground. There likely is tornado on the ground with this, purely because of how strong and tight that circulation is. When you're around 5,000 feet and you have this circulation this strong, it's a pretty good indication that you've got a tornado occurring. You could also imply too that you have a debris ball there near your Dora. Here's one. So you've got a storm that's moving off from southwest to northeast. So you've got A, B, and C. They're all spotters. Who's kind of in the safest location to observe the tornado?
A.
A. Yep.
A.
A is it. B, they're going to get nothing but rained and hailed on. I mean, they'll probably have some pretty good hail reports, but probably not the best to see the tornado. C is likely in the tornado, experiencing some probably pretty bad conditions. A would be the spot where they can get a really good idea of the storm if they're out viewing it. And that's the other thing too. A lot of these storms that we get, do occur at night, where it's difficult to spot them. Even if you are in that spot of A, you may not be able to see. You're still looking you're still looking maybe in between cloud flashes, so it can be quite difficult. Question number 6, I think this might be the last one. We're looking at a cross section of a storm. This is May 14th of 2018 out near Goodland, Kansas. So and you can see Goodland radars off to the north here. So we're looking south towards Sharon Springs. Based on the vertical cross section and the reflectivity image here, what is likely occurring? What's likely occurring in the storm, and what's something that kind of gives that away?
Hail spike.
Yep, that's one. Yep, you got a 3-body scatter spike going off down this way. That's definitely one good indicator. What's another good indicator?
You've got the two different areas on the reflectivity south of Sharon Springs that are pretty bright pink to almost white, so that's probably hail core.
Yep, that's very good. That is high, and especially too if you look at the cross section, those values are so high up. You've got 70, and these are likely 70 dBz values up above 20,000 feet. So this storm is likely producing some very large hail in this storm. Those two things there, the scatter spike and just those high values and showing them aloft are two good indicators. So we're kind of towards the end here. You know, your help with getting us reports and getting not just getting the people out there and getting the reports, but getting them kind of in the right spot and is a way where we can confirm the threat to people. Some people they're not going to take action unless they know something's occurring. So the more information that we can get, the better. And I think it is important to sometimes know what it is exactly we're seeing on radar, so that we can kind of get a really good idea of, where exactly should I have this individual look, or maybe I've got somebody in this spot, but the storm's really going to actually be closer to this person, so I'm going to hone in on them. So that's kind of why I think it's really important that we kind of go through and take a look at these. I kind of went through it, pretty fast. I did go long, but there's a lot of information there. There's a lot to take in. If you've got any questions for me, I can stay on here and answer those, or we can go back to them. Feel free to always reach out. If you see something that's looks interesting, or a feature that you're curious about, if it's during the event, just send us a little private message. If you're in chat, just say, hey, are you seeing this or whatever, or send us a screenshot or an email or text or something. But send me an email if you've ever got any questions. Otherwise, that's all I've got. And Patty, I appreciate you having me out for this, and hopefully I'll garnered a few good little tips in there, and let me know if you've got any questions.
Well, thank you so much, Mark. Appreciate your time. I already getting comments in another chat that they're getting a lot out of this, so well received.
Good, excellent. Does anybody got anything in particular, any slide maybe they need me to cover a little bit more, or anything that I ran through too fast I need to go back through?
I've got a question on your cross sections, like when you do the cross sections on your storms.
Yeah.
Where it will elevate like this one here. Is this how high it's looking into the storm? And are these different numbers that you're looking at here, are those the height of the cloud tops within the storm?
Yeah, good questions. So if I'm this particular cross section here is likely, so if I was to kind of take a drawing tool and draw right through this section where I've got my mouse. So what it's doing is then looking directly up through this whole section here. So, and it's not looking through all of it, it's just looking through the section that I drew. And you can also, too, it's kind of nice in GR, you can, once you have a cross section pulled up, you can drag it backwards or forwards. So then you could go maybe down this way or down this way. But it does indicate exactly what is occurring at that certain height. So in this particular case, your cloud top, your echo tops are about probably about 50,000 feet.
Hey, Mark.
Yes.
Can you hear me okay?
Yeah.
Okay. Back there on the hail spikes that you were showing on that one screenshot there, what side? How close was that to what we were getting over in Hartville and Houston and Mountain Grove when we had that storm a couple weeks ago?
Go back to that here. I know I had it not too far back.
I didn't want to interrupt right into that because.
Oh, you're fine. That's just fine. There we go. Yeah, are we talking about the very giant hail from?
Yeah. Yes, the ones I sent all the picture in from.
Oh yeah, that one. I have to go back and look and see. I need to pull the radar imagery from that and see what type of scatter spike we had with that storm. I know we had one. I just don't know. I just don't know what to extent. I know some spikes will show up even stronger than others, and some will show up at different heights. They won't always show up at the same height. But I know there was one with that storm. I just don't know how strong it was. And they could show up. It doesn't matter how far away the storm is from the radar. You pretty much always will get that spike if there's that large hail in there.
Okay, that's what I was wondering, because like we said, we had those big ones over there, and they're still working on replacing siding and a couple of roofs over there.
Yeah, that was bad. And in that case, like we likely had, there was likely, these pinks, whites, so the 60 to 70 dBz values. If you were to pull up a cross section, was likely up around 30 to 40,000 feet. So that hail was up so high, and it was able to just stay up there and rotate and grow and grow and grow. And it takes the right conditions to do that, but it definitely did it that day.
Yeah, okay. Yeah, we were tracking it. I had people from Seymour all the way through to past Houston there that was all online there tracking and showing the pictures as soon as they could get them. So, okay, thanks.
Yeah, you're welcome. Thank you.
Question in that regard: what would the wind speed have had to have been to keep the hail up that high, that large hail, golf ball and larger?
Probably. So one thing we look at with those supercells, you have to have a really strong updraft, and those updraft to keep that air up there, to keep that hail up there from coming down. It just has to stay up there. Typically, so the stronger the updraft, the stronger the hail. Probably between probably 50 and 100 miles an hour would be those updrafts speeds. So in that case, that storm the other day, you're probably at the high end of that. You're probably between 80 and 100 miles per hour up high. That updraft was, so it was able to just keep that thing up there and keep it growing before it eventually came down. So it's probably between 80 and 100.
Kind of mind-boggling when you think about the dynamics that go on with that.
It is, yeah. You think about it, you're at the ground, and your wind speed's maybe 10 or 15 miles per hour, but then you have a storm that's maybe 10 miles away, and you go up about 15 to 20,000 feet, and the wind's 50 to 100 miles an hour. It's just very impressive. Any other questions or comments before I let y'all go?
Thanks for doing this.
Oh, you're welcome. Yeah, anytime. We'll have to do it again. This was pretty fun. Glad the earlier technological troubles went away there, but glad to do it.
I think it was more informative in this format than it was in a normal classroom situation.
I think so too.
And I very much appreciate your time, Mark.
You're welcome. No,
and putting this together.
Yeah, no, that's good. Good feedback. Good to know. It's just doing some of these virtually. We've seen some offices do them, and lately, and I've tried to watch a few. It's just kind of a different way of doing it. I do kind of like it. It is. I could see where it is really informative, and I really appreciate the feedback there. And
he's the second one to make that comment. Heather had brought that up. She actually had seen this presentation done in Christian County and said she got more this way than in the classroom. So just so you have that feedback as well.
Okay, good. Yeah, that's good. And I think, if I did it correctly, recorded